I want to believe that today is the first day that I start the stream and everything works. Is it? It is. All right. So today's February 26, 2025 here at ASU. We're on our 7th week in CSE598. We're halfway through a module on dynamic allocator exploitation. So we're approaching the halfway point. I have a question for you guys, right? Most of you took 466 and asked me about this course. And I told you kind of how I think it is, that it's challenging, but if you succeeded in 466 and did well, it's not like the end of the world, right? Like a lot of the heavy lifting and requisite knowledge is in the 466 course. Do you guys agree? Like I accurately sold you? Cool. Because there are other people that are asking about how is 466 compared to 365, and I do think that is a fair analogy that Jan gave, but I don't know that that necessarily maps from 466 to 598. So I'm glad to hear you guys agree that we're just kind of cruising through, looking at some cool stuff. Great. I didn't include this last week, or I should have. So we finished file structs. So this is not including dynamic allocator exploitation. Overall, across the class, 90% of the file structs module was completed by the average student. Class grade on average is an 89. So that's including the extra credit. Looking good there. Now, where we are with dynamic allocator exploitation, the current module, one thing that's awesome to see is the entire class did hit the checkpoint. So right on. That's where the bulk of your value comes from time spent. But right now we're about 73% of the way through the module, which is reasonable. Like it ramps pretty steep. As always, often, there's always some spooky boss at the end of the semester. It will be true this semester as well. So if you're chilling at the 90%, know that I have something in the pipe to fix that, right? Bring this back down to a more acceptable average. Course schedule. We are plugging right along here in Heap Exploitation. We do have spring break coming up here, so we've got about a week between now and spring break. This is the planned course schedule when we started. As is tradition, I will kind of YOLO things over the second half of this course, and that begins right now. So my thought process here is I believe the students should have spring break. Like it should be a break. As I look at how we kind of move through the material, when I had the original scheduled thing, there's two motivating factors here. The persistence and botnets is a 2-week module that would run over spring break, but you'd only get 1 week of me, so you'd kind of be stuck on your own on spring break. Kind of lame, especially since it's a new module, and that means that there will be pain because there will be things that are just unknown, and it's experiment. The other thing is this relies heavily on from 466 namespacing to do networking and simulate this network. Not that you need to know namespacing, but that is the implementation detail of how we create these virtual networks that you then have to go out and mess around with. If you are by chance a TA with 365, they're doing, I believe, intercepting communications, which is also a networking simulation namespace thing. I haven't looked at their current iteration of the material, but just looking at the Discord chat, it looks like they are pork bombing themselves and doing other interesting things where they're spinning up processes and then just throwing a whole bunch of noise over the network. Since that module launched, I've noticed a slight difference in my dojo experience. And so I am going to opt for, let's not have everyone just throwing random network packets all over the dojo infra at the same point in time. I think that will just lead to less pain for everyone. So instead, what we'll do is on Friday, we'll launch the Intro to Windows Binaries, which honestly is a pretty chill module. It's not about throwing crazy new stuff to you. It is kind of what is different about Windows compared to Linux. Buffer overflow still exists. Okay, does ROP still exist? What is the same? What is different? It gets you up to ROP. It's a small number of challenges, but we can't rely on GDB. We have to learn a different debugger. We have to learn some slightly different tools. It really is a 1 week module. I'll run it through spring break, but I think you guys will get it done and have time to chill over break, which I think is the better way to go. So then we'll do the continuation of Windows after that when we come back from spring break, and then hit our botnets, kernel, and mystery content. And I think that's just smoother for everyone. All right, so kind of one of the big challenges here, and one of the things that came up in office hours last week was I'm spending a lot of time reading these POCs, right? And I don't know, I'm looking at, like, I'm spending all this time reading the POC and not writing code. Is that a fair assessment of where time was spent? A good chunk, kind of, sort of. No, I just crushed it. Okay. So you know, various opinions there. But I like that How to Heap is kind of this great database of techniques. And I think it is something to refer to and reference and do what we're doing here, but it isn't the end all be all, right? Like level 8 is challenging. I think people figured out what it's inspired by, like what POC it's inspired by, but it isn't a one-to-one exact follow this POC, right? I try and teach things not as this is, as far as like this content, I try not to be like, this is, I don't know, House of Rob, right? And this is House of Zardis, right? Like I don't, the house itself is not what's important. It's thinking about how these mechanisms work together. Like you may say, in a wider context, I used House of Spirit on, to pull this off. And somebody who does a lot of heap exploitation may know what that means. But knowing specifically House of Spirit doesn't mean that you'd be any good at like thinking about primitives in this low level exploitation stuff, which is hopefully the skill that you're practicing. Over here, in addition to kind of our complex, deeper heap stuff, which is what we're going to be poking at today, I believe off stream, I poked a little bit yesterday, not yesterday, it feels like yesterday, but last week with the fast bin. The fast bin is a singly linked list that works very similar to the Tcache. And so when you free it, does the fast bin consolidate? Does the fast bin consolidate? No, but nobody knows, right? Yeah, I don't know. I just go look at the slides. That's fair. I do it too, and I wrote the slides. But the kind of quick way of thinking about it is the singly linked list, so Tcache and fast bins. Remember, those are a lot. Everything in those singly linked bins is going to be marked as previous in use, right? The chunk after it will show that it is in use, because those are kind of caching optimization layers. So everything in fastbin and the Tcache will be in use, which means that it is not used for consolidation. So the key here in this module, the kind of meta skill, is thinking in primitives, which hopefully has been a reoccurring theme for you as we've gone through the first half of this course. When you look at the challenge, you need to ask yourself, like, is there a buffer overflow, right? Do I have that capability? Is there a use after free? I don't think I have it on here, but do I have the ability to double free? Okay? Which is separate than use after free, for the record. And then if you have those abilities, what can you corrupt? It's one thing if I have a buffer overflow that is infinite distance, right? Then yeah, it may be a long way to get there, but as long as it is something that is in front of my write point, I can overwrite whatever I want. But typically in a heap context, you have a limited buffer overflow to where maybe you can only, or not even buffer overflow, but a limited ability to corrupt metadata. And so maybe you can only corrupt, for instance, the previous size or the size, or maybe you do have a buffer overflow, in which case you could get to the pointers of a freed chunk after the chunk you're writing into. Right? So you have to think about what primitives do I have, and then what does that allow me to mess around with metadata of the heap. And once we get past that, we get kind of these more complex ideas of creating, for instance, overlapping chunks or creating chunks out of thin air. right? Creating fake chunks where we write the data such that it passes the checks and it just becomes a chunk from nothing. Good meme. So, demo plans. On stream, does anyone have any friendly stream-related questions you want me to do? If not, I'm going to corrupt some metadata, maybe draw some pretty pictures if technology works, and go from there. But I'm going to use my same kind of dummy challenge because it gives me the ability to do whatever I'd like. And then off stream, once we call time there to Twitch, we can quickly kind of run through the challenges from like 4 to 8, I think, and just play around with them and be like, well, what are these initial primitives or capabilities that these challenges have? Because one of the things that I've noticed is people are spending time making assumptions about these things, right? And if you don't understand what your kind of starting state is, then you're going to have a very hard time finding what is the correct technique to use. So we can run through some of the capabilities of the challenge to get us kind of thinking about that, and then think in terms of primitives to see if we can maybe off stream figure out what top corresponds to what challenge. So does anyone have any questions up front? Yes.
I had some questions about backward consolidation.
Okay, backwards consolidation.
Is it possible to demo it?
Yeah. Let's do something. That is the entire fun of this course. Is the question of can we demo, right? Like I spent some time before class here thinking about what I want to demo. And then I start the stream and it all falls out of my head. Wow. Did I break Twitch? Technology started off good. You want to see what I see? Any of this? Let's see. Okay, I'm going to assume that fixed it. Looks like it did. Cool. So the question was, can I look at backwards consolidation? Can we play around with this concept? So we are connected here. I'm on level 1. Do I still have... What was my cool demo? Anyone remember what I called that thing?
Heap exam.
Ooh. That looks good. Okay. So you want to talk about backwards consolidation. What is your question here?
Like I'm solving one of the levels, and I'm sure that backwards consolidation is the intended exploit. But when I'm trying to pass all the checks, when I do that, but I still sec fault somewhere. So when I free the next chunk.
See. Let's do it the other way. Let's put my script over here. I'll play around with it on the right-hand side, not let my head cover things up. User bin and Python from pwn import star context arch AMD 64. P equals process, heap example. All right. So how am I going to create a scenario that's going to like mimic what you're doing? If I want to backwards consolidate, can you get me there? Like, what are we thinking?
For my problem, we had a buffer overflow. I was thinking that I can make a fake chunk and then overflow the next metadata of the next chunk, so as to make it think that my fake chunk was already free. and then when I free the next chunk, it will consolidate it with the.
Okay. So my base case, and you please let me know if this doesn't map to what you're thinking. Because there's going to be problems here. All right, not particularly exciting, but I'm now 2 chunks. What do you want me to do next?
This will go into the pass bin, right?
So right now,
Right now it will go into,
if I were to free, it would go into the T cache.
yeah, but we need it to go into the unsorted bins.
Okay, you want to just have a bigger size? Okay. How big do you want it?
Greater than 1020, correct? So 420, like hex 420.
So the challenge doesn't understand hex, so we'll have to do a little bit of messing around there, but okay. So now you want me to free 1, free 0? Doesn't matter.
But first you will have to corrupt the, what do you say, metadata of the chunk 1, right?
I don't know. What are we doing? So backwards consolidation itself is not an active. All right. So like backwards consolidation, same thing with like forwards consolidation, but consolidation in general is just normal functionality of the heap. All right. So I'm going to add an additional chunk here because I don't want this to forward consolidate into the wilderness. That's going to cause us grief. But if I were to do this right here and then free 1, this should get, if I'm thinking about this correctly, this should put 1 in the unsorted bin. Do you agree?
Yeah.
Cool. That is what we get. So I'm going to trust that this is our 1, but we freed it. It was too big for the T cache, too big for cache bins, ends up in the unsorted bin. Right. Now, you say I want to perform backwards consolidation. So there's 2 things I need to think about if I'm thinking about consolidation. And the first is where is, right, the made up physical location. So the free chunk here is C6D0, which is this one right here. If I wanted to cause backwards consolidation, then I want this to consolidate into whatever is behind it, correct? How do I do?
You'll have to set the flag to 0, previous in use flag to 0.
So what previous in use flag?
For the chunk that we just freed in the unsorted.
Okay, so we freed C6D0. Its previous in use is set, which is indicating the thing behind it is in use. Now, you said I need to overwrite this. I could do this, right? But that would be slightly different than just backwards consolidation. Like I can cause backwards consolidation by just freeing this chunk. Do you agree?
Yeah. Yeah.
So you want to do a little bit more than backwards consolidation, right? Like if I free, we continue here in GDB, and oh no, FREE. I forgot about this. We free 0. Go back here to GDB, and we look at our bins. I got to scroll up a little bit so we can see the size of it originally. And our original output, in our unsorted bin was hex 430. It was at C6C0. In our second iteration, we see that we've moved it backwards by roughly 410, 420, hex 10, 420 bytes. It is now at C290. So the chunk here is now beginning earlier, and we see that the size is roughly double. Right?
But in this case, we get the pointer to the chunk before it, chunk 0. So what if I want to
Right? And so like right now, and is this a thing? It is a thing. Okay. If I examine 20 giant hex at this is going to be an implementation detail of the challenge, but if we look at the output here, my 0 was C2A0, and we see that C2A0 is still in the BSS. This is the pointer that is being held by my example challenge. Pointer's still there. I don't know if it'll let me use it or not. But like, I now have this. Let's see if I can do it or not. We'd be puts up above, put 0. It lets me. So this challenge lets me use after 3, right? And the pointer is not getting nulled out in my example. So that was backwards consolidation. But what are you trying to do? You want to do something crazy.
What if we didn't have control of chunk 0? Like this time you had control of chunk 0 and you just freed 0, right? After freeing 1.
Okay.
What if we didn't have control over chunk 0? It was already present.
Well, that's going to be a little trickier. So you're saying I have this. Can I not? Oh, I didn't free. So I want heap chunks. You're saying I have this. Heap chunk 0 is this, which I do not have access to. But I do have access to. So my problem here is, where is the previous in use bit located? Where is this located?
The metadata.
It's in the metadata.
It's in the size.
Right. It's part of the size, but is it before or after the allocation address?
After the no, above the.
It's before.
Yes.
Right. It's the 8 bytes before here. So if I have the ability to like write here, can I ever write backwards? No. So I don't have the ability from just this setup to change this previous in use. If I were in this exact scenario, I don't believe this is the solution to any of the challenges, just FYI. What I would probably do is create more allocations to try and get a pointer to go back.
What if you create a fake chunk inside that chunk and then override that size?
Oh, see, this started with just backwards allocation, and now we're going deep down the rabbit hole here with fake chunks. Okay. So how do fake chunks work, and what do they give me?
You just, I mean, for example, if we have 2 chunks, chunk 0 and chunk 1.
I have chunk 0. I have chunk 1.
Yeah, you can create a fake chunk inside chunk 0. That's what I'm thinking.
You said I don't have any access to chunk 0.
Oh no. So hard to explain. So chunk 0 and chunk 1 that I'm talking about are the ones that I control. And there's an allocation behind chunk 0.
Oh, okay. So okay. All right. So you're tricking me here now. All right. So let's do one of these. Okay. I have chunk 0, which is the spicy thing I'm interested in.
Yeah.
And I have control of 1 and 2.
1 and 2. Yeah.
All right.
So if I create a fake chunk inside chunk 1, which I have control of, and then I can override the metadata, and then I can override the previous in use bit. So that when I free the next chunk, chunk 2, thinks that the fake chunk is already freed. So it will consolidate it with that.
It would consolidate with the fake chunk
Yeah.
in order to make that work. That's where. Did you by chance see on the Discord my pretty picture I drew? I don't believe it's public facing, so I'll see if I can pull this up here for the Twitch stream. I don't remember the level or context that this was asked, but I do recall it having something to do with a fake chunk. Having a ridiculously long password is great until you mistype it, and then it's just all downhill from there. All right. Let's see. ASU's Wi-Fi is going to cooperate. Did you find the pretty drawing? We're racing each other here. Like I may get it on stream. If I
Yeah, I
don't,
think so. So
all right. Let's see.
you send this after office hours?
Yeah, after office hours on Friday.
Yeah, I think.
All right. So I cannot apparently. ASU's Wi-Fi will not let the technology work today. That's a shame. I can draw an equivalent of it up here. My pretty space, if I have a marker. Cool. So I have some chunk. I have some future chunk. I get a pointer here, and then behind this is my previous, and then my size. You agree? Right, this is for you, we call this 1. That's going to be this guy right here. And then this is my 2. These are right next to each other. So this is a size, and this, in theory, is a previous. Right? An important thing to keep in mind is depending upon the size of the allocation that you're requesting, this previous can be the last 8 bytes of the allocation, right? Keep that in mind. That may or may not be important in these challenges. But we have this as our setup, right? If I have a buffer overflow, you are correct that I could, for instance, create a fake chunk inside of here. And what I'm doing is this is all user-controlled data from the heap's true kind of understanding of what's going on. But I'm going to create or write a previous size. I'm going to write a size. I'm going to write a next. I'm going to write the previous. Am I dealing with large bins?
No, unsorted.
Okay. If I'm not messing around with large bins, then I don't have to care about the stuff after that. I just need these 4 values. And so I need to overflow from where I can normally write as a user to write this metadata. And then everything after that can just be A's, like who cares? I get to this previous size value. Do I care about this? Why do I care about this?
Because if you set the previous in-use bit of chunk 2 to 0, that means that it should have the previous size of the previous allocation, which is already free. So basically the size of the fake chunk.
Say it one more time. I'm sorry.
So basically, if we are setting the previous in-use bit of chunk 2.
Well, I'm not talking about the previous okay, if I set the previous in-use bit, which is chilling down here as the least significant bit of size.
So we're basically making it think that there is already an allocation which has been freed.
Okay.
So if that is the case, then it should have the previous size of that allocation.
Okay. So if we are overwriting through the previous size and we are clearing this previous in use. Twitch can't see any of that. That's why it pays to show up in person. Not my bad. I can see it. You guys can see it. That's what matters. And so, yeah, if we clear this bit and then free 2, it's going to try and backwards consolidate 1 and 2. I agree with that, right? And the trick here at the backwards consolidation is, how does 2 know where the previous thing in physical proximity is?
Calculates from the previous size.
Right. It calculates from the previous size. And so it's going to take its current location minus the previous size, which hopefully, in a normal scenario, will resolve back to 1, right? The valid allocation or valid chunk before it. And then it will verify that this equals this. And assuming that it does, we bring it all together. Yeah? But if we're trying to create a fake chunk, then we want the previous size to resolve not to where the valid chunk is. Instead, we want to make this a slightly smaller number. So when it does this subtraction, it instead resolves to roughly here, which is our fake chunk. Yeah? Now, when we write our fake chunk, we have to make sure that our size equals our previous size. Yeah? So we need to make sure that those two are equal. What else do we need to make sure?
The forward and backward pointers of the fake chunk.
Right. We also have to make sure that the next, you're using the correct term and I'm not. The forward and backwards chunks, or backwards pointers of our fake chunk pass the forward back points to myself, and then back forward points to myself. And so there's something else that I need to know in order to satisfy that second set of constraints here.
Yeah, the alloc pointer, which points to chunk 1 currently.
Okay, so what did I do? 40 giant hex at this thing. Can I use that to create a fake chunk? What's the check again?
Forward, back should point to, but it should point to the fake chunk.
It should point to the fake chunk, right? It's not just that forward back equals back forward. If we were to take a quick look, it's checking that P is forward back and P is back forward. So what do I need?
But I think I got past this.
So there's it depends on what you're doing, right? So if I'm trying to create a fake chunk, what I need somewhere that has the value P. That's in reality what I need, right? For my fake chunk, what is P?
The address of the chunk itself.
The address of the chunk itself. So in my pretty dry diagram that was on Discord, I also had some region that said BSS, and then there was some pointer, right? And we did something like this, right? Where we made next and previous point to a region in the BSS such that this resolved. But the reason that we set it that way in the context of whatever it was that I originally said is because we had this P here. That was the only reason I cared about this location. It wasn't like the BSS is special. It was that P, for the context in which I was using it, was chilling in memory at this location. And for the context that I was doing before, I believe P was here. I could be wrong. Because where does P come from here? P equals, doesn't show me. Unlink, pointer P. Yeah, P would be a pointer to the chunk. And this check would happen because this is on unlink. Unlink is when you are trying to remove a chunk from a bin. So these pointers would be valid. I'm not going to say that you can't create a fake chunk, but I can't do it without this happening. Because I'll fail this right here.
So what if I write the address of the chunk in the fake chunk itself, and
What?
then tell the forward pointer to point to it?
Okay. So if I, instead of just having a whole bunch of A's at some arbitrary location, I put the, oh, can I draw? I can't draw an ampersand. I'm going to say address of fake chunk.
I would need to write it twice.
I don't. So the statement for Twitch is I think I need to write it twice. I don't think you need to write it. You could.
Or either I can just offset it from the forward and backward.
There's maybe a one-way operation here at this marker. So just like what I did here, where I had the pointer in the BSS, I put next and previous slightly offset from each other because we're looking at this in C as forward back equals P. What does that look like in assembly?
So like
There's some base address plus some offset,
yeah,
right?
Plus 24 for taking forward and plus 32 for backward.
That sounds correct. 24, yeah, 16, 16, and 24. Did I do that right?
See.
So it should be plus 16 for next and then plus 24 for previous. And so
You want to use this?
I could give that a try. We have all the technology here. All right. I wish I just had another marker. I've just got the red. Putting our.
There are a couple more.
We have other colors. Thank you. They still can't. Twitch is just cursed. It looks like I'm writing nothing. Green the color. Oh, I'll bet you the green shows it. So this is my 1. This is my 2. This has a previous. This has a size. That's a previous, which means that there is a size back here. I just don't care. And what we're doing is we're creating a fake chunk right here. This fake chunk needs to have a size, a previous, a next, and or let's use the right words: forward, and then a back. And what we were saying is we're going to overflow this, and I said let's just throw a whole bunch of A's here until we. I got this backwards. previous size. Size. And what I need is an address of the fake chunk, right? I need that somewhere in memory. And so you're saying, let's put right here the address of the fake chunk. Just, I have this extra space, let's put it in there. You could do that. And then you'd need to set your forward to point in to yourself and your backwards to point into yourself. And that should cause this to resolve, because then when it goes forward, back, it should catch that address. And when it goes back, forward, it's going to catch this address. I don't think you need to do that in these challenges from memory, but this would work.
Isn't that the unsafe unlink exploit? How to? I'm thinking that's the intended exploit. Maybe wrong.
So we can definitely look at that specific challenge off stream.
Yeah, sure.
I'm more than happy to do that. With unsafe unlink, you are doing something like, if we were to grab it, what do I want? Shellfish, how to heap, 235. They are relying on.
I think it's the last one.
They are relying on the fact. Okay, we set up. This right here. We're creating the fake chunk inside of chunk 0. They're setting chunk 0, 1, which is going to be 0, 1. The size is going to be the size of the same thing minus 10, right? Which makes sense, or hex 10, which makes sense. So they don't have any space here. They have we set up the next free chunk, which is the forward. We don't care about the. Why do I keep writing these backwards? It's previous and then size. And we don't care about the previous value there. So it's setting the size to be the size minus 10. It's then setting the forward pointer to be, what is this right here?
I mean, this is the address where we allocate the chunk point.
It is the address of chunk 0, of the chunk 0 pointer, and the chunk 0 pointer is, in this case, in the BSS. All right. Okay. So it's the address of the chunk 0 pointer minus 24. So they're setting forward. That is going to the BSS. I'll look at that. And then over here, I have, for this diagram, maybe pointer 1. It's just chilling there. We set this to be here such that there's 24 bytes. And then the back pointer, we set it so that there's, what is that, 16 bytes? See if I can math. I can math. So that means both of these are pointing to somewhere so that they resolve to pointer 1. Okay. So then that's what those two are. We have our fake chunk forward, our fake chunk back. Those are both pointing to slightly behind pointer one in the BSS. We assume we have an overflow in chunk 0, so we can freely change chunk 1's metadata. That is, in this case, 1 to 2. Makes sense. What are we overwriting here? We are setting, they call it chunk 1 header. Chunk 1 header is, the chunk 1 pointer minus the header size. So that means that we are currently looking at previous. Chunk 1 header. Boop. Is going to be, they're setting the previous size to malloc size. What is malloc size?
I think that's the
Hex 420 here.
so I think they assume that the chunk was hex 430, so they do minus hex 10. So then I think they write something.
I agree that's what they should do, but
Yeah, I think they write it below that, the print state.
I don't see where this is getting set.
Right below malloc size, that if we have, if the chunk one dot previous size could have been hex 430.
If we normally had free chunk 0, chunk previous size would have been hex 430. In this case, 420. Okay, yeah. Because chunk size is an allocation size. They're allocating hex 420. Okay, that makes sense. Yeah, they're allocating hex 420 right here, but the chunk size is going to be hex 430 because of the metadata there. And so then when they put the previous size to be hex 420, that does result back to our fake chunk. All right, that makes sense. If we had normally free, blah, blah, blah. Chunk header 1, they are ending it with 1. If this is our chunk 1 header, index 1 is going to be the size. They're ending with 1. They're setting the previous in use, which is what you hit us with there. They then free chunk pointer 1. And at that point, chunk 0 overwrites itself to point to an arbitrary location. And that is where the other part that I pointed to in the on topic Discord, where I grabbed the unlink code and then I grabbed like 4 lines of, it's like the first like 4 or 5 lines of the unlink code. You can see what it's setting and how it's working. It actually isn't. It isn't really about creating a fake chunk here. They're using a fake chunk to write, to overwrite this value is what they're doing. I can see if I have this on here. Do I have how to heap or safe unlink? No. Okay. Git clone. Shellfish. Like I could throw GDB on it. glibc 2, 3, 5. Unsafe unlink. We would GCC user bin GCC no PIE unsafe unlink. And then I need to patch elf. I need to use the same. Same libc and same loader. Okay, so that should be the challenge here. I should have built it with symbols, but whatever. We're gonna. This thing just has a main function, right? Yeah. What I care about is probably this stir copy. So let's disassemble main. We get around. Okay, so it's not going to be a roster copy. There's the moving the A's with new values. What I care about is this right here. This free, is it the last free? It's the last free. Can I find the last free? Yes, main plus 597. Okay, so this is where we are. This is where we are before the magic happens, right? We've set all of this stuff up. We have our fake chunk. We are about to free something. If we, back to our context here, about to call free, and we look at RDI, we're about to free 56D0. 56D0 is this one right here. And so when we free this, I'm sorry, I'm reading this backwards. 56D0, which is this one right here, its previous is not in use. And then if we were to look at this right here, and we examine, what do I want? 4 giant hex at that address minus 10. What we see here.
Can you print a bit more so we can see the forward and back?
You see, okay. So this isn't. That right? 5060. Did I grab the wrong one? 5060, 5680. Oh, okay. You want.
No, that's right. That's the forward and backward pointers for the page.
Yeah. Yeah. I know. I thought it was. So this is what's about to be free, 56D0. This is, for our diagram, this chunk right here. This is the true size of the chunk, which is why 56D0 has a size of hex 430. It's getting it from this value, this location right here. This is the size of the chunk. Now, the fake chunk that we've created is offset by hex 10. So this is the size of our fake chunk that is really 8 bytes into the real chunk. We then have our forward pointer and our backward pointer. The important thing here is our forward and backward pointer. These are pointing to, if I examine, let's do 8. It's going to be a bit more than what I need, but what we'll see here is this is 8 past, 16 past, 24 past, right? And then that's our backwards pointer. And so that's 8 less. And so both of these will result to this address right here, which you are correct is that guy and not the fake one. So I guess it isn't getting that. That bothers me. But what's going to happen here is in part of the unlinking. Do I have the code here? P forward equals. Oh. Okay. Forward equals that. Forward back. Back. That's not the right exact section of code that I want. Can one of you look at the Discord real quick and see what it was I linked to? Like roughly what the name of the function was that I
Unlink chunk.
just unlinked chunk. Okay. Okay. So the interesting part here is this right here. So if back equals pointer back, then back is going to equal, or back equals p back. P is, or fake chunk. P back is going to be this address. Where am I? This -10. This is the address of back. And when we set back forward equal to forward or forward back equal to back, what ends up happening is we end up getting a pointer to here. And so when I step through this and come out the other side, I imagine this is going to just look like garbage. We end up with writing, we're writing this to itself. 404048. Gosh dang, where was it? That just changed, didn't it? 404048. Context. Because what you get is that you're getting a pointer to the BSS. So that way the next thing you overwrite can be up here in the allocator. You're questioning. And I'm failing to show. This is, oh, that's 2A. I want, okay, that's why I'm goofy. I want to examine the 40 giant hex at the address of the Alex struct. Oh, this thing doesn't have an Alex struct. This is their demo. They called it what? Up at the top.
Chunk 0.
Chunk 0 pointer. Do I still get this? Okay. So now if I heap chunks, and where's my 4040? This is that, which is the address of the chunk 0 pointer. And that's why down here, chunk 0 pointer is now pointing where we want. and we use it to overwrite our victim string. So then when we just did this free, chunk 0, 3. This doesn't map one-to-one to the challenge, but you're thinking about it right. What you end up with is a pointer into here that allows you to corrupt this. Anyone that's done that, do you agree? That's what you end up with. They are separating the victim from the overwrite. Is what they're doing here with their POC. But you have the right idea. Did this help at all, or did we end up in a circle? All right.
The only problem is that like yesterday I was trying out the first method where I write it in the fake chunk itself, the address. Yeah.
Oh, you're trying this?
Yeah, and I don't know, I messed up something probably.
So the problem here is you'd have to know where you are in the heap. Do you know that?
I can just it's the PI is not enabled, right? So I can just check where that.
So there's no PIE, but where's the the heap's going to be? Yeah, I guess you could do that.
But then when I tried it the second way, I didn't get any errors, but it just segfaults at free. So
It never segfaults just at free. It's segfaults deep
deep
inside.
Yeah.
And if you were to slowly step your way through, you would find the metadata that it's checking. Like, my guess would be that like one of the forward or backward pointers wasn't correct. I get what you're doing there. We could try and do that if you want. But let's take
probably off.
Let's take a break first. So let's make Twitch go away for a few. So welcome, I guess welcome back. That little starting soon message here is a bit of a troll. We are midway through having a conversation about the heap and various things going on, and we just took a nice break there where I elaborated on my pretty drawings. Okay, so while I was hiding, somebody said, "Hey, I'm on level 4." I started looking at it, and I haven't really spent any time yet tackling it, but let's go from there. So, hopefully, we don't solve this thing. Fortunately, the heap challenges are a little bit harder to accidentally have the flag fall out. So let's see what we got here. Level 4 says perform various heap operations, some of which may involve the flag. Challenge can manage up to 16 allocations. Okay, I think that's just a boilerplate because we have that on most of them. What's something that you might try right now? Like, what's something I might want to know? What is your first step? I have this unknown thing. What do I want to do?
Try send flag.
Try send flag. I like it, right? It's what I do as well, right? When I first start working on a challenge, I just start like typing things in it and being like, what can I make this thing do? A normal person or a sane person might open it up in a decompiler. That's not me, right? I'm glad that's not you either. Send flag says not authenticated. All right, so that gives me some idea of what's going on. What else are we thinking here?
So, like from what I attempted, like first I tried this, and then I opened the decompiler, and I thought of seeing like why it's showing.
Oh, okay. So you started with send flag, right? You went rogue like I do, but then immediately we're just like, oh yeah, no, this right here, I need to investigate further and figure out why. Uh, personally, I would have just typed the other commands, but it's all I just like seeing what happens, right? Twitch says, yeah, I'd poke it with a stick, right? It's I think part of the fun is in the exploration. But I do agree that no matter how much stick poking, occurs here, um, there will come a point where you need to look at it in the deep play there here. And so you said I looked at send flag, and I want to know why it says unauthorized. See if I can find it. Send flag. All right, we get if authenticated. Does that answer our question? Do we know more?
So it's set to false for now.
Okay. So it's set for false now. What is the next question I might ask? I might be thinking about.
So like I double clicked on it, and it is in PSS, and
Good.
we know that we get to know its address. So I know that some.
So do I know that this is valid right now? The statement was I double click because I want to know where in memory is this. I see it's in the BSS. That's great. Now you made a statement that may be true. I don't know, but we haven't proven it yet. Is this address always like universally correct? You guys should know this. The answer is no. Well, why is that not always a constant? It's because binaries, we have ASLR now, right? The defining factor on whether the BSS is a static value or not is whether or not it was compiled with PIE. We can run checksec on the old challenge, and we see there is no PIE. So now we conclusively know that that is a constant value that I have, constant memory. I just like to be complete because otherwise someone could look at it and be like, oh, Ida says this, on some other challenge. And yeah, I didn't mean to and accidentally trolled them. Okay, so we know this is in the BSS. We know that the BSS is a constant memory location. What is our next plan of attack or kind of thought?
Need to like set it to something that is anything that is not 0.
Okay, we need to make that thing not 0. We probably need to use the heap to do it because that's really all we get to play around with. Okay.
I went to the how to heap page on GitHub, and I like searched for like what I thought was bright might be involved because we need to write to the memory. And for bright, I think after that I was just looking at the unsafe unlink dots because I think that this might be used, but
Okay.
I don't.
So we know that we need to do an arb right. I agree. Like based on what we see here, that may make sense to me. I either need to set that authenticated value, or I would need to somehow direct control flow to jump like in the middle of that function and bypass that check. Right. In either cases, arb right is probably the primitive that I need here. Now you said that you jump to the shellfish how to heap, and that's good. That is what the bearded fella in the video says to do. However, there's a lot of things in here, right? And so if you just get to clicking, then you're like, all right, well, which of these can give me arb right? Probably most of them, right? The heap exploitation is largely about getting a pointer, right? Getting the heap to return an arbitrary pointer to you. And whether it can be used for arbitrary read or arbitrary write depends on whether I call read, right? Safe read. Do we know what this thing does?
Yeah, it like we can write to the memory location that we.
Yeah. I forever manage to name things counterintuitively. Then safe read reads from standard in and writes to your memory, right? Similarly, puts will allow you to specify an index, and it will puts at whatever that pointer is, right? So if I get the heap to return a pointer of my choosing, do I have an arbitrary right? Yeah, because once I get malloc to return that pointer that I choose, I can just call safe read and I'm good, right? I can write whatever I want there using safe read. If I get malloc to return a pointer of my choosing and I call puts, well, now it's an arbitrary right. Right? And so the fact that it's an arbitrary right and the fact that I'm on the heap, right now, the possible things for me to look at is everything. Right? Like, so I mean, a couple of these are like how safe linking works, which won't actually allow you to return a pointer. But that's a lot of stuff to run through, right? Are there any other restrictions or pieces of information about this challenge that we might want to investigate? So I, so that I kind of naively like just running things, right? We just kind of YOLO it. If I malloc 1, it says, oh, you can't. And this is where somebody, I think last week, tried to call me a Star Wars fan, but I'm not. I'm sorry. Star Trek is better. I said it. So this BB-8 matters, right? This is a new piece of information that will heavily influence what I'm looking for when I look at these talks. Why does BB-8 matter? It says you can only allocate things that are larger than BB-8. So we got to think about it in terms of the bins, right? While it's not included in this slide deck, BB-8, I believe, is bigger than the feed cache. Yeah. BB-8 is bigger than what I can do here with the fast bins. So I can't go there. Can BB-8, an allocation of BB-8 end up in the unsorted bin. Yeah, it could. So I'm looking for a POC that maybe it interacts with the unsorted bin, or I'm looking for a POC that interacts with large bins. BB8 is also big, so it doesn't go in small bins, and everything else ends up in the large bin, right? So I really only have two bins that I can mess around with here. I can mess around with the unsorted bins. I can mess around with the large bins. And I'm looking for an arborite. Now you like this guy, unsafe, unlink. Why? I know we talked about it a little bit, but why do you like this guy for this one?
So basically, if we just go to the master page of how to heap, then the arbitrary right, I just search for right basically.
Oh, okay.
I just hit command and I so
That's a totally reasonable thing to do. I have never done that. There's.
and I mean in right also like arbitrary right was only in front of unsafe unlink, so I started exploring this and that's where I'm at.
All right, that's totally reasonable. This could just be because I've been in computer science long enough that I'm cynical about stuff. I don't trust people's documentation, right? Like documentation is great, but totally logical way of dealing with it. I see how you got there. I like delving in the details, but let's take a look here. So we're on 235 unsafe unlink, which is what we were rambling about earlier there. Now we can wheel out the old picture here. And then I see that you said something there, Twitch. Give me just a second. So this was our great voyage of unsafe unlink. Twitch says, well, if you're going to poke it with a stick, you eventually need to tear it apart, but at least one poke. And I know the state I would want to find while looking in the source. Okay. So I poke at it and then look at it in the decompiler. That's ultimately where people end up. Now, this was our like unsafe unlink scenario, right? There were a couple things that I needed, and we could derive that from reading this, but we spent some time here already. So I'm going to hopefully be able to get there from our pretty picture. What do I need to pull off this unsafe unlink? I need to have two allocations I control. I need them to be physically right next to each other. Yeah. What else do I need? So we got to think in terms of like primitives and powers here. Twitch adds documentation claim stuff, but you need proof. Yeah, I don't trust the docs. I also a lot of times don't even trust source anymore. Right? There's only assembly, and even that lies sometimes. But I need to be able to overwrite this. I need to be able to write this previous value, right? I have to be able to create a fake chunk, and I need to be able to touch this size guy. Yeah. Can I do that in this challenge? I don't know. The answer may be yes. You may have gone down a path that works, but it was unintended. I try very hard to not allow unintended solutions, but it's actually way harder to write something that's vulnerable in only the way you want. So what I want to look at here is when I do safe read, what does this thing check? Because I need to be able to write, remember the size value here is outside the bounds of the allocation, right? The last 8 bytes of the allocation is dual use. When the chunk is allocated, it's whatever the user data is. When it's not allocated, it is the previous size, right? but the size of my next chunk, right? The 8 bytes here, this is outside of the bounds of what Malik intended me to write to. You agree? Okay. And so if we look at safe read, it says provide an index, which is fine. We could specify index 1, right? And get to we could create this scenario and we could specify index 1. And then when it calls read on size A. Do we control size A? Well, size A is, well, that's messy. Thank you, Ida. Size A is some offset from this V11. I get to see what this V11 is. Okay. So I scrolled up until I just was looking for where's V11 referenced again, right? I haven't found its definition. That's fine. Alternatively, if you like being efficient, you can highlight a variable and hit X, and it'll show you everywhere where that variable is referenced. But I just scrolled up because I'm a simpleton. And I saw here that when we malloc something, that same memory location, right, V11 plus some offset, where this offset here is, willing to bet that it's my index. Yeah. If we look from D5's use here, it's the index. So the size is stored from when we malloc. So if I create an allocation that's 100 bytes in size, then when I do my totally named correctly safe read, I can only read in 100 bytes. So I can read all the way up to this spot right here. But in order to do the unsafe unlink, I have to be able to corrupt the least significant byte or nibble, I'm sorry, least significant nibble of the size value. So I need to go 8 bytes further. That means I actually can't do it. The unsafe unlink is close, right? And this is where like that small little difference in what powers you have, what is the specific nuance of the POC matters a ton, and why we need to start thinking about things in terms of do I have a buffer overflow, right? So in order to do the unsafe unlink, I need to have at least 1 byte. I need to be able to overflow by at least 1 byte to touch the size value of the next chunk. And I can't do that here. Does anyone disagree? I look forward to someone finding something that I overlooked, especially with this new challenge, right? That I have drafted.
Is it live?
Is it what?
Is it live?
No, it's not live. It'll be live tonight. I'll ping you guys in like on topic or something. No, I have it. It's on the dojo. I just want to run it a few more times and think about it to see if there's something like super trivial that you guys can do to get around it. I don't think it's like crazy hard, but it's just another different. So we need to think about what powers we have on the onset, right? And so right now, it was totally valid to go through that workflow, right? Control F, I'm going to trust the documentation, and the only thing that says right is unsafe unlink, so it must be that. They lied. Right? There must be another way. So what do we know about the challenge we said? Well, I want to get some pointer. I want to be able to write to it, and I know I'm restricted to large bins, unsorted bins. Yeah. So if instead of trusting the main page, we're back to here. What looks like it might be relevant? I said we can mess around with the unsorted bin and the large bin. Do I care about safe linking? Safe linking is something we covered in a different module, but it applies to the fast bins and the T-cache. Do I have access? Do I care about the fast bins and the T-cache for this challenge? No. Do I care about something that's called fast bin dupe? No, probably not. It probably has something to do with fast bin. Fast bin dupe consolidate. No, probably not. Fast bin dupe into stack. No, probably not. How about fast bin reverse into T-cache? Nope, probably not. Like we can click on all, right, and we can see. But I'm just gonna trust that maybe they named at least the bin correct. Right? They might. They did be there. Not a dig specifically on this repo, but just in general, right? Developers are horrible at naming things and explaining things. Okay, House of Bot Cake. I have no idea what a bot cake is, right? That one, all right, maybe. And so we click into this and we give it just a quick once over here. What is it doing? Well, I see that they are allocating things to fill up the T-cache. And it says that, right? We're mallocating to fill up the T-cache. Is this probably something that I want to go further? They're doing things with small sizes. They're messing around with the T-cache. And then okay, well, they are adding something to the unsorted bin, maybe. But I don't think so, because everything that they're doing.
It says it relies on double free, and we don't.
Oh, does it say? Does it say that? I just missed it.
Yeah, the third put state.
Aha. So we need a double free. Is double free something I can do in this challenge? I didn't check. We can find out real quick. So we'll find what happens here when I call free. Actually, it looks like I could double free. Interesting. I'm okay with it, but anyone want to tell me why I say we could double free? Look, I can get this. What stops me from double free? Well, what am I looking for here? What's the correct developer behavior?
They should set the address to 0
Yeah.
as well.
Yeah, I should null after I free the pointer. I should null it out, right? Since it's not nulled out, I could type free 1, and I could type free 1 again, and in both instances, it would call free on the exact same address. So there is a double free, which is something we didn't know. But a House of Bot Cake is probably not what we want because it is interacting with small allocations here. We're doing the T-cache. It's the T-cache and the unsorted bin and the relation between those. So probably not that. We could go to Ein Hajar. Did you see it?
I'm just reading the print statements instead of the comment at the top.
Yeah, we're doing something with the T-cache to do something, so that's probably not related to us because we can only do BB8 and larger, right? House of Lore, right? But you see how like we can look at it and we get a ballpark and say, okay, does like what they're looking for roughly match what I'm looking for? And we can do that. I'm gonna make a bold assumption here. All right, this was a big number. No exception, large bins and unsorted bins. There's one of these that's called large bin attack. Oh, I can mess around with a large bin. So let's see what that thing looks like. So what does the large bin need? Large bin what do we see here? It prints off a whole bunch of stuff. Sometimes help text is actually not helpful. Right? It's hard to parse what's going on, but we're mallocing. We have P1. Why do we not P2? G1? Oh, guard. Okay. So we have some big allocation. We have a guard allocation. We have a big allocation. We have a guard allocation. We're freeing this first one. We're mallocing something bigger than the first one.
Move the stuff into large.
Yeah. And so everything from here to here is just moving this chunk into the large bins. Because this, when this guy has a guard, this guy has a guard, this gets freed, so it's in the unsorted bin. And then when we malloc something larger than that, it's going to the large bin. So far, this is all stuff we can do. Right? There's nothing here that says we can't. All right, we're like halfway there. All right. What's next? We free the second pointer. All right, so now that's in the unsorted bin. We have one in the large bin, one in the unsorted bin. So far, this is all stuff we could do. At this point, yes. Okay. Now, this is something that I don't know that we have. What is this? What is the primitive that's going on? At this point, we freed one, we freed two. And then we are writing to the memory of P1. So that's an additional like power primitive that we haven't checked for. Anyone want to tell me what that would be? So it is a write, but it's like a use after free, right? I need because we've already freed P1, but I need to be able to write to overwrite the metadata of this chunk when it's free. And we haven't looked at the challenge to see if we can do that yet. Well, we kind of did when we looked for the double free, because we know that when freed, the pointer isn't null, right? We saw it. So that means that the pointer is still hanging around. And we had that safe read function. Does safe read do anything to stop me from writing to this pointer after it's been freed? No. So I do have use after free. I can write to this pointer after it's been freed. So then when I am going back here to the large bins, and we see this, can I do this right here? The answer is yes. I could free that chunk, and I have the ability to overwrite that memory location. Okay. Then they are calling malloc. I have the ability to call malloc on big things, so I have that ability.
P1 and P2 are chunks.
So the convention here, and it's one of the tough things when you're trying to parse these, is I don't believe these were all authored by one person, right? I think many people authored this, and so the coding styles are going to be slightly different. But if we look here, what I kind of gather they're doing, P1 is the pointer that's returned from malloc. So that is the allocation address. And then G1 is going to be, like I call them guard allocations. It's a malloc call. The only reason this exists is to protect P1 from consolidating forward. But as we kind of step through this, was there anything here that this POC does that I cannot do in the challenge? So then the question is, well, what does this pot give me? I probably should have looked at that. All right. What was the goal of this whole thing? It looks like this act allows us to overwrite a target address. So we're corrupting the metadata of the large bins. The assertion, as far as what the POC is proving here, and what do we get is that we can set the target address or the value at target. And target is probably just some global here. Okay, in this case, it's on the stack, but it's some memory location that is initially set to 0. Right? We can set it to P2 minus 2. So we can take some 0 value and we can set it to some non-zero value. When P2 was our pointer of the second allocation up here, malloc 2. Yeah. Now it's not setting it to 8 bytes because it's casting it as a size T. So it's really kind of a weak primitive, right? It's give me memory location, and I can set it to a value that we don't really control, but it's a non-zero value. Because it's taking the pointer, is that right? P2 minus 2, P2 is a, what do they have that as? Oh, size T star, okay. But they aren't dereferencing that. So yeah, it's going to take the pointer, subtract 2, and then just the first 4 bytes there, since they're casting it as a size T. So it lets us set a 0 value to a non-zero. That's the extent of what our power is, because I can't control P2 minus 2, the value that's there. Is that sufficient for me to pull off this exploit? You say no? What is the challenge check? We started off with just send flag, right? Send flag has a authenticated value that is 0 initially, right? That's why we're failing and it's saying no. Yep. This POC, wrong one. Where am I? This POC lets me set a target address, which could be the authenticated value, to a non-zero value. If authenticated is 1, am I authenticated? Yes? If authenticated is 42, am I authenticated? If authenticated is 6034, am I authenticated?
Any
value that isn't 0. What does this POC let me do? Set a target address to a non-zero value. That is sufficient for me to pass that authenticated check. So it took a little bit of time, right, and a little bit of hunting and clicking, kind of iterating through this. But the nice thing is if you take notes, right, on what these POCs are, you don't have to duplicate that work, right? What does House of Bot Cake do? What bins does it interact with? Tcache and unsorted bin, right? If I wrote that down, that's because we clicked on it a little bit ago, and so I looked at it, right? What is House of Einjar, right? When you look at it, take some notes on what bins need to be interacted with, then you don't have to duplicate that same work. But for level 4, then there might be another one, but because it is restricting us to large allocations, I jumped to the large bin attack, stepped through it, and then verified, does this, is what this thing is, what this is doing, can I replicate that in the challenge? The answer seems to be yes. And then is it sufficiently powerful for me to obtain the flag? I think this one is.
I could not understand the last statement, like the assert statement. What the left side part, like size t p2 minus 2. What does this mean exactly?
So you agree that target is this size t that's chilling on the stack, right? That is initially set to 0. Okay. So then the next question is, what is p2 minus 2 cast to a size t? Well, p2 in this case is a size t pointer. Size t should be 4 bytes, but it's a point. So when I subtract one, when you do pointer addition and subtraction, you're incrementing and decrementing by the size of the thing you're pointing to. Personally, when I work with pointers, I like making everything a char star because everything is just literally bytes, right? In this case, that's not what we're doing. So if I were to say P2 plus 1, it would be the address of P2 plus 4 bytes. If I say P2 minus 1, it's P2 minus 4 bytes. So when they say, or they like the address of, right? P2 minus 2 is going to be the literal value that is returned from malloc is P2. I subtract 2 from that pointer, but it's a size t pointer, so it's going to be the literal value that is returned by malloc minus 8. This is what this will be. But then they pass it to a size t. So instead of being an 8-byte address, we're going to truncate it and just get the first 4 bytes of the pointer that is returned by malloc minus 8. I agree that it is a very terse syntax, and depending upon your comfort with C, you can definitely be wondering what's going on, right? That's where, just like I did with the, I think, unsafe unlink, we could copy this, we could throw it onto the dojo, we could compile it, we could throw GDB at it, and we could break and print this stuff out. Like we can, what was this, large bin? Hopefully I don't have to fix the libc and this POC just works. Someone says, would large bin be large enough to cover our nibble? It doesn't matter how large the large bin is. If you can only read the size of the allocation, you'll never be able to touch that nibble. That nibble will forever be just out of reach. Okay. And so this isn't using the exact same version of libc, right? Dojo reasons, but the POC still works. And so I threw the POC up here. I just compiled it. I did it kind of quick, but I compiled the C code from that spot. And when I run it, we get the benefit. I like reading the source, but it certainly can help. You see, what did target become? In this case, target became 16036E0. And if we were to look up, does it say where P1 is? Was it P2? 16036E0. Oh, P2 minus 2. P2. Yeah, no, that should be. Oh, okay, yeah, P2, not P1. Okay. So it became P2, not P2 minus 8? Why did they do that? P2. Oh, they're printing. Okay. They're printing P2 minus 2. So I was right. It has to do with what they're printing out, whether we are printing. In this case, they're printing off P2, P2 minus 2 because they're printing the chunk address. And what I said was P2 minus 8, where P2 is the allocation address. And so we're all correct. It's all just a matter of how we want to think about it, whether we start at a allocation memory or we go 16 bytes behind and say this is the beginning of the chunk, right? It becomes this like semantic how you think about it thing. But yeah, and so what happens is they are setting it in this case because of how it was compiled. It's the first 4 bytes of P2 minus 2, but they're calling it P2 right here, which is why we see 16 036E0. I don't really care if, like I said, if this was 42 or if this was 1006. I just care that it's not 0, right? Not 0 is enough to make something that is false true. I mean, that's really all I need to pass the check on this challenge. Cool. All right. Twitch, it's been fun. I from my feed, I'm still just a spinning disc, so I have no idea what you saw. Hopefully it was at least a little bit entertaining. With that, I will end the stream and help out whatever people got for me in detail that I can't show you. Goodbye, good luck. I will see you next week.